If you look up at the night sky and, find Mars, um, you're looking at a world that we have mapped in stunning high-resolution detail.
Mm-hmm.
We know its craters, its valleys, its ancient dry riverbeds. But if you walk down to the beach and just look out at our own ocean, you're looking at a profound mystery.
Yeah.
Welcome to Science After Dark. Tonight, our mission is to do a deep dive into the darkest, coldest, and, well, most highly pressurized environment on Earth.
Right.
An environment where, as of 2023, only about 25% of the seafloor has actually been mapped to modern standards.
It's incredible.
I mean, more than 80% of our own ocean remains completely unobserved.
It really is a humbling check on our technological ego, I think. We've had 12 human beings walk across the dusty surface of the moon, but fewer than 10 people in the entire history of our species have ever reached the absolute bottom of our own ocean. It's the largest habitat on the planet, and yet it is our absolute last great unexplored frontier.
Okay, let's unpack this. Because how do we even begin to grasp something that big?
Right.
We hear stats all the time like, the ocean covers 71% of the Earth. But those are just flat numbers.
Mm-hmm.
The horizontal scale is one thing, but the vertical scale is what completely breaks my intuition.
Oh, absolutely. That vertical scale is where the real alien world begins. The average depth of the ocean is roughly 3,700 meters.
Okay.
That's over 12,000 feet straight down, and that's just the average.
Right.
If you drop into the Challenger Deep, the lowest point in the Mariana Trench, you're descending nearly 11,000 meters.
See, I always try to picture Mount Everest for this.
Oh, that's a good way to look at it.
Everest is like the absolute limit of the sky for us, right?
Yeah.
8,800 meters up. If you ripped Everest out of the Himalayas and just dropped it into the Mariana Trench, the summit would still be hidden under 2 solid kilometers of water.
Yeah.
It's just wild to think about.
It is. And as you travel down that massive vertical column, the rules of physics and biology they change completely.
Mm-hmm.
It's helpful to imagine taking an elevator down a miles-high inverted skyscraper.
Right, where every few floors you drop, the environment gets a little more extreme.
Exactly. So the top layer, down to about 200 meters, is the epipelagic zone.
Okay.
The sunlight zone. This is where photosynthesis happens. It's the ocean we know, coral reefs, schools of tuna, dolphins.
The familiar stuff.
Yeah, roughly 90% of all marine life is packed into this incredibly thin top layer.
Because that's where the food is, right?
Yes.
Sunlight equals algae, algae equals small fish, and small fish equal big fish.
Precisely. But as your elevator passes 200 meters, you enter the twilight zone, the mesopelagic.
Right.
The light here is incredibly faint. It's too dim for plants to grow. But it is far from empty. It actually hosts the largest animal migration on the planet.
Really?
Yeah. Every single day, billions of organisms commute vertically. They rise toward the surface at night to feed under the cover of darkness, and then sink back down into the twilight zone during the day to hide from predators.
So it's a massive daily elevator ride just to survive.
Exactly.
But eventually even that twilight fades, right? Once we hit 1,000 meters down, the last scattered photons of sunlight vanish completely.
Mm-hmm.
We hit the midnight zone.
The bathypelagic, yeah. And it just keeps going. From 4,000 to 6,000 meters, you hit the abyssopelagic zone. The abyss.
What bigger?
These are vast, flat plains of mud and sediment. And here's a staggering fact for you. Those abyssal plains make up about half of the entire surface of the Earth.
Really?
Yeah.
Half of our planet is a freezing pitch black plain of mud.
Yeah.
That's deeply humbling.
It is.
And then the literal rock bottom, the Haddle Zone inside the trenches, dropping all the way to 11,000 meters.
Right.
Which brings me to the physics.
Yeah.
As we drop into the midnight zone and beyond, the temperature hovers just above freezing. The sunlight is entirely gone. But the real boss down there is the pressure. I was reading that it increases by 1 atmosphere every 10 meters.
That's right.
So by the time you hit the Challenger Deep, you're experiencing roughly 1,100 times the atmospheric pressure we feel here at sea level.
It's incomprehensible pressure.
That's around 8 tons per square inch.
It's enough to crush a standard submarine like a tin can.
So,
Hmm?
how is anything biological surviving that? I mean, if 8 tons per square inch can crush engineered steel, how does a fish with a beating heart not just turn into a microscopic pancake?
Well, by abandoning the architecture that surface life relies on.
Okay.
For starters, you can't have rigid air spaces. A swim bladder, which surface fish use to control buoyancy, would just collapse instantly.
Oh, sure.
So deep sea animals don't have them. Their bodies are mostly water and highly flexible tissues, and water is, relatively speaking, incompressible.
Okay, but even on a microscopic level, pressure that high messes with chemistry, doesn't
Yeah.
it? Like, it would literally crush the shape of a cell.
Yeah. You hit the nail on the head. That is the true danger. The extreme pressure literally forces water molecules inside the internal structures of proteins.
Oh, wow.
Yeah. A protein is basically a complex folded string of amino acids, and its specific shape dictates its function.
Right.
When the pressure forces water into those folds, the protein unfolds. It collapses. The literal building blocks of life are being crushed.
So they need a way to keep their proteins folded correctly.
Exactly. And the solution is an ingenious molecular adaptation called piezolites.
I love this concept. Explain how piezolites work, because this just blew my mind when I was reviewing the biology here.
It's fascinating. Basically, piezolites are small organic molecules that act like a chemical scaffolding.
Okay.
They bind tightly to the proteins and physically brace them. This prevents that forced water from getting inside and unfolding them. They lock the protein structure in place against the weight of the ocean.
It's literally like putting up steel support beams inside a building before a hurricane hits.
Yeah.
But, on a microscopic level, their cells are structurally fortified.
That is a perfect analogy. And this adaptation is so consistent that scientists can actually predict how deep a fish lives just by measuring the concentration of piezolites in its tissue.
You're kidding.
No, the deeper they go, the more scaffolding they need.
That is brilliant. Okay, so they've solved the pressure problem with chemical scaffolding, but they are still living in a world completely devoid of sunlight.
Right.
And yet, one of the most surprising things about the deep ocean is that it isn't entirely dark. It's actually full of light, just biological light.
Right. Roughly 76% of deep-sea animals are bioluminescent.
Wow.
They produce their own light through a chemical reaction within their bodies, usually involving a light-emitting molecule called luciferin and an enzyme called luciferase.
Okay.
It's essentially the same mechanism fireflies use, but in the ocean, it's the absolute dominant source of light.
Okay, here's where it gets really interesting to me. If I'm a small, vulnerable fish swimming in a pitch-black abyss full of predators,
Yeah.
turning on a glowing blue light seems suicidal. It's like strapping a neon sign to your head that says free lunch. Why risk producing light in the dark?
It seems completely counterintuitive, right?
Yeah.
But what's fascinating here is that bioluminescence is beautifully paradoxical. It solves the exact problem you're worried about.
How so?
Let's look at the twilight zone. Many predators there hunt by swimming below their prey and looking upward.
Okay.
They're trying to spot the dark silhouette of a fish against the incredibly faint residual sunlight coming from the surface.
Oh, I see. So if a fish swims above them, it blocks out that faint light, and the predator sees a shadow.
Exactly. So to survive, many prey species use a tactic called counter-illumination.
Counter-illumination?
Yeah, they have light-producing organs on their bellies, and they precisely match the intensity and the wavelength of the faint sunlight coming from above.
That is so smart. It's like, imagine you're standing in a dark room looking out a dimly lit window.
Yeah.
If I stand in front of the window, you see my dark silhouette. But if I tape a flashlight to my chest and shine it at you with the exact same brightness as the window, my silhouette just vanishes. I blend in perfectly.
That is exactly how counter-illumination works. They are painting themselves with light to become invisible.
Incredible. But what happens if they do get spotted?
Well, then light becomes a weapon. Some deep-sea shrimp and squid can eject a cloud of glowing bioluminescent fluid into the water.
Like an ink cloud, but glowing.
Exactly. It acts like a flashbang grenade to blind and disorient the predator while the squid escapes into the darkness. Others use it as a burglar alarm.
A burglar alarm.
Yeah. If a small fish is grabbed by a predator, it will flash brilliantly. It's essentially screaming for help by lighting up the predator.
Oh, wow.
The hope is that the flashing light will attract an even larger predator to come and eat the thing that just attacked it.
The enemy of my enemy is my friend. So we've got this incredibly complex visual language of chemical light. But creating light with chemistry is one thing. The discovery that completely shattered our understanding of biology was the revelation that the deep sea could create food with chemistry.
Oh, absolutely. The 1977 Galapagos Rift expedition. This truly is one of the greatest paradigm shifts in the history of science.
Set the scene for us. Because up until this point, the absolute golden rule of biology was that all life on Earth depended on the sun.
Without exception. I mean, plants use sunlight for photosynthesis, herbivores eat the plants, carnivores eat the herbivores.
Right.
Even in the deep ocean, the assumption was that any life down there was just feeding on marine snow.
Yeah.
Dead organic matter slowly drifting down from the
Like
surface.
scavengers.
Exactly. Scientists expected the deep sea floor to be a barren, muddy wasteland. So in 1977, researchers take the submersible Alvin down 2,500 meters in the Galapagos Rift, entirely focused on mapping geology.
And out of the pitch black, their lights kept something that shouldn't exist.
They found hydrothermal vents. We call them black smokers.
Okay.
These are towering, chimney-like structures on the seafloor, violently erupting superheated, mineral-rich fluid from beneath the Earth's crust. And the water temperature coming out of these vents can reach up to 400 degrees Celsius.
Hold on. 400 degrees. Water boils at 100 degrees.
Oh, yeah.
How is this not just instantly turning into a massive steam explosion at the bottom of the ocean?
It goes right back to the pressure we were talking about earlier. The immense hydrostatic pressure, hundreds of atmospheres pushing down, it physically prevents the water molecules from expanding into a gas.
Of course.
So it remains a superheated, highly toxic, acidic liquid.
Okay, so you have toxic 400-degree water billowing out of the seafloor in pitch darkness. Not exactly a prime vacation spot.
Except they found dense, lush ecosystems thriving right on the edge of these boiling vents.
Wow.
Giant tube worms with blood-red plumes that grow over 2 meters long, fields of massive clams, swarms of blind crabs and shrimp, an absolute oasis of life where life was thought to be impossible.
So, where is their food coming from? I mean, if there is no sunlight, there is no photosynthesis, there are no plants, how is this entire ecosystem surviving?
Through a process called chemosynthesis.
Okay.
If we connect this to the bigger picture, the battery powering this ecosystem isn't the sun, it's the geothermal heat of the Earth itself.
Oh, wow.
At the base of this food web are highly specialized bacteria. These bacteria take the toxic chemicals billowing out of the vents, specifically hydrogen sulfide, and they use the chemical energy to convert carbon dioxide into sugars.
They're literally eating toxic chemicals and sweating out sugar.
Exactly. And those bacteria feed everything else, those giant tube worms you mentioned.
Yeah.
They don't even have mouths or a digestive system.
What?
Instead, they have an internal organ completely packed with billions of these chemosynthetic bacteria. The worm absorbs the hydrogen sulfide from the water, feeds it to the bacteria, and the bacteria feed the worm from the inside out.
So these ecosystems are essentially running on a completely different battery than the rest of planet Earth.
Yeah.
And we found more since then, right?
Yeah.
In the 80s, we found cold seeps where methane leaks from the ocean floor, and even whale falls, where a sunken whale carcass becomes a massive decades-long feast for completely unique deep-sea worms and bacteria.
We have.
Yeah.
And the implications are staggering. If life doesn't need sunlight, if it just needs liquid water, a heat source, and chemical nutrients,
Right.
then our search for extraterrestrial life changes completely. We don't just have to look for surface life on Earth-like planets.
Oh, I see where you're going.
Life could be thriving right now in our own solar system, in the subsurface, pitch-black oceans of Jupiter's moon Europa or Saturn's moon Enceladus gathered around hydrothermal vents.
By looking into our own oceans, we found a blueprint for alien life.
Exactly.
And honestly, the creatures we are finding in the deep sea look entirely alien. What blows my mind is just how recently we're actually seeing them.
The timeline of discovery is incredibly compressed.
Right. Take the giant squid.
Yeah.
The literal kraken. We've known they existed for centuries because their dead bodies would wash ashore, or we'd find their massive beaks inside the stomachs of sperm whales. But humanity did not film a live giant squid in its natural deep-sea habitat until 2012.
It's wild.
The bioluminescent anglerfish, first filmed alive in 2014. And just a couple of years ago, in 2022, a camera in the Izu Ogasawara Trench recorded a snailfish swimming at over 8,300 meters. The deepest fish ever filmed.
And the scale of what we don't know is even larger.
Yeah.
In 2023, a study was published about the Clarion-Clipperton Zone, which is a massive stretch of the Pacific Ocean floor. Researchers cataloged over 5,500 species living down there.
Wow.
And an estimated 88 to 92% of them were entirely brand new to science.
We are discovering alien species faster than we can name them.
Literally.
But here is where you need to tie this back to the biology, because this 2023 species discovery connects perfectly to a very controversial study that just came out in 2024 regarding dark oxygen.
Oh,
And I really need to push back on this concept gently, because it honestly sounds like science fiction.
the dark oxygen debate. It is thrilling, but yes, highly controversial.
So we established that chemosynthesis allows organisms to make food without sunlight.
Right.
But respiration's a different story. If there are over 5,000 species down in the Clarion-Clipperton zone, they all need to breathe oxygen. I always assumed that oxygen was made by plants near the surface and then slowly circulated down by ocean currents. How is it conceptually possible that oxygen is being generated at the bottom of the ocean without a single plant in sight?
That was the assumption. But researchers studying the Clarion-Clipperton zone noticed oxygen levels actively increasing near the seafloor. They traced it back to polymetallic nodules. These are potato-sized lumps of rare metals like manganese, nickel, and cobalt that are scattered across the abyssal plains.
Wait, metal rocks in the mud are producing oxygen?
That is the hypothesis. The idea is that these metallic nodules might be acting like natural geobatteries. Because they're composed of different metals, they carry a small electrical charge. The researchers propose that when these nodules are clustered tightly together on the seafloor, they might generate enough of a natural voltage drop to literally split seawater, H2O, into hydrogen and oxygen gases through natural electrolysis.
So you're saying a field of metallic rocks might be generating enough natural electricity to zap seawater and release breathable oxygen bubbles into the pitch dark.
Exactly. No sunlight, no biology required, just raw geochemistry acting like a battery.
That's amazing.
Now, this is fiercely debated. Many scientists want more data, questioning if the voltage is truly high enough to sustain this. But if it's true, it means the deep sea is fundamentally capable of producing its own breathable oxygen.
That is absolutely wild. And it perfectly brings us to why these polymetallic nodules matter to us up on the surface.
Right.
Because those nodules aren't just scientific curiosities. They are the exact reason that the deep sea is suddenly in the crosshairs of global industry.
Yes. We are talking about deep sea mining. Those exact same nodules, the ones that might be generating oxygen and supporting these fragile, slow-growing ecosystems, are packed with cobalt, nickel, copper, and rare earth elements.
Which are the precise materials we desperately need for electric vehicle batteries, solar panels, and smartphones.
Exactly. There is a massive economic push at the International Seabed Authority to begin scraping the abyssal plains to harvest these metals.
Wow.
And the environmental concern is massive. These ecosystems operate in the cold and the dark. They grow incredibly slowly. A single plow track from a mining machine through a field of nodules could destroy a habitat that might take thousands of years to recover.
That's heartbreaking.
We are risking damaging the planet's ultimate frontier before we've even finished mapping it.
It feels like an impossible race.
Yeah.
And to even understand what we are risking, we have had to overcome terrifying engineering challenges just to look at the seafloor.
The human element of this story is a testament to our drive for discovery and our willingness to face unforgiving physics. In the early 1930s, William Beebe and Otis Barton built the bathysphere, a hollow steel ball. They bolted themselves inside and had a crane lower them on a single steel cable into the pitch black off Bermuda.
That is terrifying. Just dangling from a wire, looking through a tiny quartz window, knowing that if the cable snapped or the seals failed, the pressure would crush them faster than human nerves could even register the pain.
But it pushed the boundary. By 1960, Jacques Piccard and Don Walsh took a heavily engineered bathyscaphe, the Trieste, all the way to the Challenger Deep,
Right.
nearly 11,000 meters down. They heard an outer window literally crack under the pressure on the way down, but they kept going.
But what really stands out to me is what happened after that. They reached the bottom in 1960. And then nobody went back for over 50 years.
Yeah.
Why the massive gap? If we had the tech in 1960, why did it take until James Cameron's solo dive in 2012 to return?
This raises an important question about safety and capability, because it is staggeringly difficult and expensive, and the physics simply do not forgive mistakes. In 1960, it was a brute force engineering feat. To make it repeatable and to actually do science down there safely required decades of advancement in material science. We needed the invention of specialized syntactic foam for buoyancy, advanced titanium forging, and remote robotics.
And even with modern materials, the margin for error is absolute zero. We all saw the somber reality of that in 2023 with the implosion of the OceanGate submersible, the Titan.
Yes.
5 people lost their lives instantly during a dive to the Titanic wreck.
It was a tragic reminder. At those depths, the pressure doesn't give warnings. It exploits microscopic flaws in a hull, especially experimental composite materials like carbon fiber, in milliseconds.
Hmm.
It forces us to constantly weigh that beautiful human drive for discovery against the lethal, uncompromising realities of physics.
So what does this all mean? With all the risk and all the expense, why keep pushing? Why do we need to explore this dark, freezing environment when we have so many visible problems up here in the sunlight?
Because our fate on the surface is intricately tied to the depths. The deep ocean is the unsung anchor of our entire climate system.
Right.
It absorbs 25 to 30% of all human carbon dioxide emissions. It absorbs roughly 90% of the excess heat from global warming.
Wow.
Deep sea sediments are among the largest carbon stores on Earth. Without the deep ocean acting as a thermal and chemical sponge, our surface world would be unrecognizable.
Not to mention the biomedical potential.
Yeah.
You've got organisms evolving unique biochemical pathways to survive extreme pressure and toxicity.
Absolutely.
Compounds found in deep-sea sponges and microbes are actively being studied right now for novel antibiotics and cancer treatments.
It is a treasure trove of biology. But it is deeply threatened, not just by potential mining, but by bottom trawling, climate change, and incredibly plastic pollution.
Oh, right.
We have already found plastic grocery bags resting at the very bottom of the Mariana Trench.
That is just a heartbreaking irony.
Ugh.
Human trash has reached parts of the planet that humans themselves have hardly ever visited.
Yeah. It is a delicate, ancient world that is far more fragile than its crushing pressures would suggest.
Well, as we wrap up our late-night descent, I want to bring it all together. We've journeyed into an ocean that covers our world, plunging miles into darkness, where the pressure could crush stone. A place where fish literally stabilize their own cells with chemical scaffolding, where life cloaks itself in bioluminescent light to become invisible, and where vibrant ecosystems thrive around boiling toxic vents, completely isolated from the sun.
It is the engine of our climate and the silent keeper of our planet's deepest mysteries.
It is. I want to leave you with one final lingering thought for the night. For centuries, we have looked at the deep ocean and places like it as inherently hostile,
Right.
as barren, extreme environments trying to kill us. But if the crushing pressure and utter darkness of the deep ocean actually hide the most species-rich, dynamic habitat on our planet, what incredible solutions or life-saving discoveries might we find if we stop viewing extreme environments as hostile and start viewing them as cradles of unseen potential?
That's a beautiful way to look at it.
Something to mull over as you drift off.
Thank you for joining us in the dark. Wishing you all a very good night. And signing off, this has been Science After Dark.